Hello, Edgar. Hola. Okay, I'm ready to share the screen. Okay. Thank you for your patience, guys. My students in Houston are going through what you guys were a week ago, which is prepping for the midterms. So there's our Monday. So and Tuesday, and so they were nervous and asked for a little extra time. The exams are all graded. I'm missing exams for a handful of people, and it's probably because they got caught and I scanned them and misplaced them or something. I scan all the exams, otherwise it's like 3 feet tall worth of paper that I have to carry back and forth, and I just can't do it anymore. I mean, one year I had a suitcase, and then, the guy said, "Señor, ¿qué es en su maleta?" Son examinaciones. ¿Por qué? Like, so when they start making fun of me there, because I know all of them, I'm there every week, then I decided, okay, I got to get another approach here. So I bought a really cool double-sided scanner. It does it in one pass as fast as I can feed it in, creates color PDFs. Awesome. So your exams come out looking terrific, so I can show you what they look like. Let's see, scans. So here's what one of them looks like. All right, so I can grade them, make notes, etc. So I don't have a paper exam I can give you back. I have to give you back a PDF file, and I need the Becario's help to help do that. So what I may do as a option is next time give you the physical exams back, and we'll go over the answers. You just won't have any marks at all on any of your exams. They'll just be exactly like you gave them to me. Okay, so, and then you just turn them back into me before you leave class that day. But back to the missing ones, if you showed up with sin calificación and after the first examinación parcial, then it's because I'm still looking for a few, and I doubt there are a few people I know did not take the exam, because there's a few names I've never heard, I don't ever recognize, but probably it's my fault. So don't panic, because I think there were more in this class than the other two sections, but the grades were higher in this class as well. So yeah, so that was nice. If you did end up getting something below a 70 by some means, I gave you a 70 because I don't want you showing up on any list, and I think that's like the list cutoff point. And everyone's grades go up as the semester goes on. Everyone's, every year. So there's more stuff, partly because I monitor and give people plenty of chances to add points to their totals for things, extra credit problems or stuff like that. All right, so give you a chance. And then some people, I had one student last year that I was contacted by somebody at the university who asked basically, is this person in trouble? We saw their scores, and I said, there's no way they're going to pass. They haven't shown up to this. They haven't shown up to that. I'm super flexible on dates to turn things in, but, this is ridiculous. And so I think they're going to fail. And they got a B. You got to be kidding me. Because I guess somebody talked to them and basically said, all right, this is it. Fail this and you're gone. I don't know. I have no idea what they said. But whatever it was, it worked. And they ended up doing great, which was like a fantastic success story. I love those kinds of stories. Do not try that. Okay, please do not take that path, because I think maybe after thinking about it last night, that may be part of the ingredient that made the department decide to be much more strict with deadlines. So they're like, how did he get a B? I have no idea. I'm guessing. But it pays to be paranoid. It's served me well my whole career. So I'll mention that to you guys. So at any rate, we had left off in the middle of this box, remember? So this is what goes on inside the source computer. Today we'll look at what goes inside the router and what goes inside the destination computer as well. But this is an area where it will be cool to understand this in detail, so you'll first of all, know more than everybody else at any cocktail party of TCP trivia. And I, also believe that it will remove a lot of mystery. You'll actually know what's going on. So just to recap, this is layer 3. We're in the network layer in this chapter. So the layer up above hands the network layer things that it wants to send on the internet. And so there's some exceptions. If you send something to your loopback address, it makes it down to here and just turns around and goes right back up again. That's for testing. That's a special IP address that everyone has that you send things to, and it will reflect it back. It's used to, among other things, make sure the network stack is on and running, and it's also a way to test things, to test programs, to make sure they're correctly sending things down to the network layer. So this upper layer is, let's say, TCP. So here's my data. I send it the length of the data and the destination address. Those are the two key things. And the destination address is the IP address of the destination, not the name of the destination. All right, so we entered the network layer. If you recall, we packetized the data. So this is now formally a full-blown IP datagram. So it's got 4 fields in it that we're going to be concerned with here. It's got IP and MAC, not port numbers, but this time we're going to look at layer 3 and layer 2 because that's all that's left. So we build it here, and this is filled in, and this is filled in already, source and destination. This is me, and this is like the website I'm going to. And my MAC address is like built in. Somehow I managed to rescue that. It sort of still looks like built in. So the only spot I have left, you guys remember this? Is this one here? So when I get down to the next layer of inside my network block, and I hand it the destination address, and it hands me back the next hop address, I have no place to put it. If I put it in here where destination IP addresses would normally go, then what's going to happen is it'll make it through, out my computer, and it'll get to this router, and the router will go, oh, mission accomplished. It's reached its destination. I guess we're done here. But you're like, that's not the website I was trying to get to. In fact, you're not even a website. You only go up to layer 3. You don't even know what a website is. Right? So that won't work. So what we do instead is take advantage of the fact that we're positive of one thing for sure, and that is whatever this next hop address is, it's on our LAN. We're guaranteed of that. The next hop is something we can hop to. It's not the next marathon. It's not the next hops. It's the next hop. One hop away. You don't go through any routers. It's on the local LAN. So I know it's somewhere inside of this. And in this silly diagram, the only thing that's inside of that is the other router. So if it's on the LAN, I have another way to reach it because I can just use its hardware address. I can see the hardware address of everybody on my LAN, but no further. I can never reach a hardware address outside my LAN. It's impossible. So I can reach this guy, and I ask ARP to give me his MAC address. And ARP may have to leave my computer, send its own traffic out on the network, figure out if this person's alive, if they respond. If so, please tell me your MAC address, etc., and before it can give the answer back. Or it may already have it stored from paying attention before. But either way, once I have the MAC address, then that's what goes in here. And now I can deliver this packet to the next hop. The only thing that will change in the next hop is we're going to use this as the source, and this is the destination. And then at the next hop, we'll use this as the source, and this as the destination. Every time, both addresses have to be on that local LAN, whichever LAN it is, right? So in this case, the very first one, this was me, and this was the destination. So you go hop by hop by hop, and make your way across the internet. When you're on the last one, the destination address says basically it's on the local LAN. So, use the destination IP address. And at that point, finally, you feed ARP this IP address. Does that make sense? When you're at the last router, the IP address whose MAC address you're looking for now really is the destination. You hand ARP this one. This is an IP address, and he will hand you back the destination web server's MAC address. So this works beautifully. So it takes sometimes 100, often dozens, at least 10 on average, of these lookups as packets make their way across the internet. Hop by hop, both ends for every packet in the world, every day, every second, billions a second. This is done. So there's a lot of compute power that goes into just doing this stuff around the world. Okay, so that's how I get through here. Where we stopped was at fragmentation. So sometimes what you send to the next device is too big to fit on the network. We talked about ATM networks and how they only accept 53-byte packets and 48-byte payloads. That's really small. So if your program handed TCP a message, it could be 8,192 bytes, not uncommon. TCP would break it up into individual segments of 1,500 bytes apiece, roughly, and it gets its way down to the data link layer, and it's going over a network that has an MTU set to 250. So I'll define the acronym that I just threw at you in a second. So the MTU is the maximum size I can use. So it's going to have to be broken up. So what will happen is you will take the full IP header, and the full IP header very often includes some options, some optional fields that are filled in, and the payload. And the payload is going to have a TCP header, let's say, and the TCP payload. Well, TCP can call it his payload, but the whole thing is IP's payload. So it will take this and do the following. It will take the header with the options and duplicate first in one packet only the whole thing. IP header plus options. In all the rest of the packets, it will just put the minimal IP header. And the number of packets is going to be based on, of course, how much it has to bust this thing up into how many pieces to make it fit. And the rest of these packets, and I'm going to just switch it to the blue here, and the rest of these is going to be payload part 1. Actually, payload part 1's up here. Part 2, part 3, part 4. 1, 2, 3, 4. It's like taking a loaf of bread and running it through the slicing machine. And you're just going to send it piece by piece. Somebody at the end can put it all back together. So this is what has to happen if your packet is too big. Okay, so they're trying to figure it out, so I'm going to give them a sec. Got questions? You good? ¿Tiene preguntas o no dudas? No? Okay, all right. So, I don't care what language you ask questions in. If you don't understand something, stop me and say it however you like. Okay? Okay, so this is something that's done automatically. In this particular example, it was done by the source computer. Usually you will implement IP to not have to do this because normally you also wrote TCP, or at least the same operating system vendor included both of them. This is part of your OS. So Microsoft can't claim like, wow, we don't know how to talk to TCP. It's like somebody else. Like, no, it's yours too. So what will usually happen is they will tell TCP, hey, when you got that 8,192 byte message from the program and you had to break it up into segments, make them smaller. Don't make them any bigger than this. And then I don't have to fragment. Well, like, why should I? Like, I'm your big brother and I told you to do it. Just do it. Okay, I'm sorry. So it'll break them up into smaller ones and send them down, and then you don't have to do fragmentation. But that doesn't solve the problem of getting you out of harm's way, because fragmentation can happen at any router along the way. At any point, you can get to a router where the next hop it needs to take won't take packets as big as you've got. And so the fragmentation would have to happen inside the router. And exactly the same thing will happen. Now, one thing we haven't talked about at all is one of the things in the IP header is a serial number. And it's generated by IP, and it's assigned, and I want to see if I can find a picture of it. I don't think we got to one yet. And I don't know if they actually included it in here. Let me pull up one, and I'll show you what it looks like. Oh, wow. Hands on the wrong keys here. Okay, IP header. Okay. This might work better. It's not a pavo real. That one I recognize as a person, a human being. Well, I've heard it all coming from this window, let me tell you. I mean, I've had them like blow my head off. The birds were so close and so freaking loud. I jumped up out of my chair, and that was the first year. Then I got used to it. The students loved it, and they thought it was just like fantastically funny, and of course it was. Okay, so here's a picture of an IP header, and I had to draw this thing because I couldn't find one that I liked, and so I have it as a PowerPoint, as an Excel spreadsheet too. But one of the things in here is this 16-bit identification number. So this is like a serial number. And every time the network layer of your computer manufactures an IP packet, like it's coming off the assembly line, it gives it a serial number. It doesn't care who it's for or where it's going to or if it's a retransmission, anything like that. It's not a sequence number. It's one layer below that. It's a serial number. So Sue, bye.
Thank you.
See you. So it'll something I said. Come back. We were going to make espresso. It's a line from Young Frankenstein. Sorry. So every IP datagram it sends out the door, it gives the serial number. Right. So every IP datagram leaves with that. If I have to fragment, every one of these pieces will have that same serial number in it, so that you know which ones to put back together again. If they have like different serial numbers, how would you know they're supposed to all be assembled together? The other thing that happens is you have some bits in this. Hello? Oh, it was PDF, sorry. You have some bits that you can set in here as well, and we'll talk about them later in another chapter, but they tell you whether this is a fragmented packet or not. So if you see a datagram come in and it says it's a fragment, and you look at the serial number, you put it in a pile with all the other fragments with that serial number until you have them all together, and then you rebuild exactly the packet that really was sent to IP and hand it up a layer. That's the way that's going to work. So this was considered bad. Fragmentation considered harmful, I think was the name of the paper. English, we use, you guys should know this if you don't know this idiom already, some blank considered harmful is constantly used in technology fields because it's mocking like the government's declaration finally in the 1960s that cigarettes considered harmful. Now, do you guys know who Fred Flintstone is and the Flintstones, the cartoon and stuff? You know, between parts of the Flintstone show when they would go to commercials, Flintstones advertised cigarettes. Did you know this? Fred Flintstone, the cartoon character, would come out smoking and would like advertise Chesterfield cigarettes. I'm like, what? Are you kidding? So by the time I was born, they'd come out of the closet about tobacco being bad. And they did it. But as just to constantly prod them, anytime somebody's got like a position where they want to try to convince people and it's been debatable, they'll use that phrase. So fragmentation considered harmful. And so what they've done with IPv6 is they've prohibited it. What you're supposed to do instead is send out exploratory packets that will result in an error coming back, kind of like traceroute forces an error coming back, if it reaches a point where it has to be fragmented because it cannot. So it will stop there, but it's just a probe packet. It's not your real data. And then you try again with a smaller one and see how much further you make it. Then you try again. And, you know, router managers are like, screw that. I'm not doing that. So they send the smallest packet possible. So let's look at the logic. The logic was that routers don't have enough time to manage fragmentation. They're busy. They're very valuable. Like, okay, we got it. You're very important. We're very impressed. So we don't want you to have to waste any time doing fragmentation. So we're going to eliminate it because we want you to focus on routing. And then you look at the repercussions with IPv6. If all people do to avoid fragmentation is just to send the smallest packet possible anyway, then you're guaranteed to be generating more packets than necessary. With me so far? Because if you could have put more data into each packet, it would have taken less packets to send. So you're generating the maximum amount of packets possible to send the data, which adds more or less work to the routers. More. Like, so it didn't really work. So that's, IPv6 is full of ironies like that, where, you know, people have to like think through it logically. They're very smart, smarter than me, but there's some things that I just can't figure out what they were doing. It also, it's been 25 years and it's still less than about 5% adopted around the world. So I don't know about you, but if you can't get more than 5% adoption with the thing that was supposed to be the savior for the internet after 25 years, you failed. Mm-hmm. They're using it now for things. It's very helpful, but it was clearly not needed the way people thought. So we're not perfect at this stuff. We screw stuff up and make bad protocol decisions. And Google basically turned their back on TCP last year, which was stunning. Well, 2 years ago now. And we'll talk about that a little later. So now I've got myself out the door, and I send whatever it is, one fragment or all fragments. And in fact, everything passes through this fragmentation phase. And if you look at the definition of this, every packet is a fragment. Some packets are the first fragment in a stream, and some packets are the last fragment in a stream, and some packets, most packets, are both the first and the last. In other words, they're not fragmented, but we call them fragments anyway. So every packet has, you have to look at the fragment bits and figure out if it's the first, and if it is, then you have to figure out if it's also the last, and then if it is, then you're done. You just send it on up. Okay, so let's take a look at what goes on inside the router. It has less work to do because it's not dealing with applications. It checks the integrity of a datagram when it receives it and discards it if it's corrupted. Now, it doesn't have a checksum inside of IP the way some of the other layers do. It just has one for the header, but not for the payload, which is kind of funny. Why would you not have one for the payload and just have one for the header? Why would you do that? It takes longer, so the size is a factor. You have to wait for a huge packet to show up. You can calculate the IP header as soon as you know what the header is, right? But why, I mean, do we not care about the payload, its integrity? Isn't that what is yours part of it? Isn't your stuff in the payload? Yeah, well, where is it then? It's got to be down in there. Like, inside IP's payload is the TCP box. Let me go back to this diagram. All right, so this is my IP datagram in red, and this blue part is what you handed IP that you wanted delivered. It's the data. So we all know it's going to be like a UDP packet or a TCP packet, and in this case I use TCP as an example, but your data is in there. This thing started off with a message from your application. It was sent to the transport layer, and then sent to IP. So at IP, if you go to the description of the header, IP adds all this garbage to the top, but then what follows is this blue box. It's your stuff. So it's kind of funny because they'll do a checksum, but they're only going to do it on your stuff, on their stuff, not on yours. Well, that's kind of rude. So don't we care? Don't you care about my data? IP, I've already dealt with your evil brother UDP. So yeah, we do care about the data. But who checks the payload? So you'll find this answer will point to some things that we see in other places in the stack as well. So it turns out what you can basically answer is just another layer. Someplace else checks the integrity of the data. So Ethernet checks, and that's for sure. Boy, does it. And it checks the whole frame. And the transport layer does a checksum on the entire packet as well. So a layer below and above are checking it. So they just decided overkill. Don't need to do it. It's going to get checked by the layer above. So they only check the checksum. All right, one of the things we didn't really talk about in Ethernet is that the header checksum checks not only, in fact, this is, I have to remember how to get this exactly right because we're going in the opposite direction that the other textbook I teach from goes. They start at the top and go down, and sometimes I get a little lost. It's so important to these protocols that the header for IP not get corrupted, that there's a layer that includes the IP addresses, which aren't even part of its layer, in their own error calculation. And so we'll see it when we get to TCP, but we'll include parts of the IP layer in our checksum as well. We're that concerned with the integrity of it. So the header checks its checksum itself, but we're going to do it too, because we're nervous about the packet being sent to the wrong host or them thinking that it came from the wrong host. So we're going to include it in a higher layer. That's sort of like wearing suspenders and a belt. You really don't want a mistake. All right, so back to our diagram. Inside the router, we check the integrity. Then we find the next topological address, just like we did before. It's guaranteed to be on the local LAN, or the destination is on the LAN. So this is either going to hand us the next router, or it's going to tell us, use the destination IP address, you're done. No more routers. So you'll grab that hardware address. In this case, this won't matter. There's no fragmentation. You'll send what you've got out the door. Most of the time, you'll be going through more routers, and so you'll look up the number here. So I told you I was going to define the acronym for you. This stands for Minimum Transmission Unit, and you can actually change this. So you remember I've used the analogy like it's easier to get a small car on the road than it is to get a big car on the road. Smaller things, there's more small spaces left than there are big spaces. So, you know, if you're going to move, if you ever moved houses, you put the big stuff in the truck first, and then you put the smaller things around it. If you put boulders in a tall glass cylinder, and you don't have room, let's say they're this size, you don't have room to put another one in, you can break one into sand and put several more in, because it'll just go in the spaces between. So the same is true. It's just a natural analogy. The same is true here in the network. So you can actually change your MTU in most operating systems. And it's something you can do if you're seeing in Wireshark lots of dropped packets and fragmentation errors and retransmission requests and things like that. Wireshark will show you the ones that it sees. And they show up as red or black, for example. And if you see those, then one of the things you can try, if you think it's something local on your network, just try sending smaller packets. You can force it yourself. You may force fragmentation to occur, but that doesn't matter. And so how would you do it? Well, on a Mac, there's a control panel option. It's the network settings on Windows. So I can come up here and go to my advanced settings and go to the hardware. And, oh, this is also fun. Here's my MTU. I can make my MTU 512 bytes if I want, and change it. And it will immediately start sending smaller packets from this computer. It will never send another packet bigger than 512 over that interface. So if you're having problems, it's worth a shot. This is going to cause Cisco a lot of extra work because the WebEx packets that get sent out are bigger than this, and so they're going to get fragmented, and Cisco has to unfragment them. So I'm going to hold off on doing it right now. We can try it at the break, pull up Wireshark, or when we're pretty much done. If you guys want, just somebody remind me if you want to see it. So what happens inside the destination computer? It's got almost nothing to do. It will throw out a bad datagram, so we know it'll do that, and it will depacketize. Everything runs through depacketization. If it finds that a packet is not the first and last, but it's just the first or just another fragment, it will store them and give a chance for all of them to show up. This can cause big performance problems because if you lose a segment, then you got to start over. So let me describe what that means. Oh, maybe we could do it with this one. Suppose this guy gets dropped, and it turned out there were 100 of these. You can't rebuild this blue square. It's impossible. You're missing this piece right here. It got lost along the way. So you broke it into 100 pieces. 99 of them made it. 100 of them made it all the way until the last router. And the very last router out of, let's say, 25 routers drops the second one. All the rest show up. What's going to happen now? So you're going to store these. Are you going to store them forever? Why will you not store them forever? So what's the first thing I think of as an evil attacker if you tell me you're going to store them for a long, long, long time? Do it over and 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 always leave out packet 2. And so you're going to just fill your memory up more and more and more with almost finished packets. And I'll crash you. I'll crash you. I'll fill up all your memory and you will crash. So you have to think paranoid, always, always think like, how would this be a vector of attack? So if we don't let it take a long time to do it, there must be a good reason. And that's one of the most important ones. So that's what's going to finally throw this thing in the trash. But meanwhile, what's happening at the layer above with TCP? You guys learned this in 2018, both the year and the class. What's happening at the next layer up? What's it expecting to receive? What is the next layer above, guys? What? Louder? Nope, we're at layer 3. We're at the network layer. Transport layer. So what's the transport layer expecting? Especially if it's like TCP. Yeah, but what do we call it? It's got port numbers. Remember the name of the datagram's this layer. Anybody remember the name of the one up above? Segment. Ding, 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 ding. Winner, winner, chicken dinner. So segment is the right answer. So it's hard, right? Nobody uses these words. And like when you leave here, you'll never hear people use that. Nobody ever talks like that. They all call them packets. And packet is not ever a word in the definition. It doesn't even exist in the 5 layers, which is like crazy. Then why do we call it that? So we borrowed it from what the switches do. They're packet switches. And we don't even call packet switches that anymore. We just call them routers. So it's just funny the words that we hold on to. So it's expecting a complete intact segment. What's not going to happen when he doesn't get that segment? What will he not be able to do? What does the transport layer normally like to do when he gets a segment? Check it, and what else? Is that as far as the segment's ever going to go? He is the transport layer, so what's the transport layer supposed to do? Thank you very much. Get it to the application. So he's not going to be able to do that. And what else does the transport layer do to let the other sister transport software running at the other end of the network know what's going on? What does it send back? An acknowledgement. Do you guys remember acknowledgements? He's not going to send an acknowledgement. What's the sender going to do when he doesn't get the acknowledgement? Resend. Yeah. So is he going to just resend number 2? This guy right here? He has to. He has no idea this even exists. He sent IP this. This is what he's expecting to get the acknowledgement for. This is what he made a copy of. This is what he set a timer for. This is what he'll retransmit. So you're going to force 25 routers to redo work that they did right the first time already with 99 packets, and you're going to force 24 routers to do something they did right with the 100th packet, all because the last guy blew it on one of the packets. So that's another complaint about fragmentation. Okay, well, I complained about the paint I used to paint my house last year. That'll change both of them about as much. Complaining will do nothing. We need fragmentation because all networks are not the same size. At the core of the internet, they've standardized on lots of things, on using 10 gig circuits, aggregated up to 40 gig circuits, especially undersea. There's tremendous amount of fiber right now. We only use maximum 10–15% of what the network's capable of, which is like mind-blowing to me. But people poured a lot of money into bad investments, but they left the fiber behind. So we get to use it. But standardizing all that does a lot of things, like it means you don't have buffer mismatches, you don't have bottlenecks, and you probably don't have to ever fragment. So they upgraded the core to IPv6 way early on. So those routers all run IPv6 in the backbone core. So that's why you don't see lots of hops in the core backbone, because it's invisible. Your IPv4 is tunneled through it. So we'll talk more about tunneling again later. So I depacketize it. I store the fragments. If they're all there, I reassemble them. If it's true that all the fragments arrived because this is all there ever was in the first place, then just send it directly up to the app through reassembly. But everything has to pass through here, so everything's treated like it's a fragment, including packets that are not fragmented. So there's a reassembly timer. You set that, and if it goes off, you throw everything in the trash. No more timers for you. Come back 2 years. Seen that Seinfeld episode, the soup Nazi? He gets mad at Jerry. No more soup for you. Come back 2 years. 2 years? Really? What did I do? So yeah, it was a funny one. And there actually was a guy in New York like that inspired the story. He didn't say like, don't ever come back to my store. He just picked this large arbitrary time. Please leave and do not come back for 14 months. Let's make it 14 months. Do not come back for 14 months. What? What formula are you using for that? Okay, so we'll talk about some more issues related to the network layer. Some services are provided by auxiliary protocols, and we'll talk some more about those. Like we've already know about ARP, but that's an example of one. Error control is an interesting topic. There is error checking, like I told you, at the Ethernet layer, and then I suggested it was very good. And there's some error checking in the layers for transport and for the application maybe can add error checking, like if you're adding encryption, like with HTTPS, there's some error checking there that goes on. But we just saw IP doesn't really have anything. It really doesn't have much to offer. It'll do a header checksum, and that is error checking, but that's about it. So, famous paper got written at Stanford about 10 years ago, and it had to do with, let me see if I can remember any part of the title at all. TCP error. Let's do it this way. I would like to find the paper. Problem is I've amassed so many papers that I don't remember the names of them anymore. Damn it. So it's just gonna drive me insane. I'll have to just wait for it to happen again. Let's see. OS errors. I wonder if it's this one. Nope. Yes. Could it really be? Is there a Cisco author in here? S.H. Alum, I think, is the Cisco scientist. How old is this damn thing? It looks super old, doesn't it? It's not that old, but I think it may be it. It only focuses on OS. It's a later paper. I'll see if I can find it. Became very famous because it became very infamous. It was a shockwave. What they set out to do was figure out, okay, so how good is this all working? So like, if we have all this error checking, then we shouldn't have any retransmissions because of packets failing this check. They should all be valid. In fact, it's so unlikely that an Ethernet frame would even ever make it this far if it was buggy, that there should be basically 0 errors. So what Ethernet does is it takes the packet from IP as it's leaving the computer, it's going down the layers. It takes the packet from IP and builds an Ethernet frame with it, and it calculates an error checksum, an ECC code, and it puts it at the very end of the frame because it's flying. It's got to go at hardware speed. So it does not have time to queue the whole thing up, calculate it, and then stick it in a special field. So it lets the whole thing go by. It's adding it as it goes by, calculating it, and slaps it on the tail as it goes out the door. So that's one reason why, that's the reason why Ethernet is the only layer that has a tail as well as a header. So what's this tail do? This tail does something that numerically is fascinating. And I'm going to spend an extra minute on it with you guys because we tend to go a little bit faster on stuff. Partly because you guys answer my questions. Not always. You could be better, okay? But you're pretty good at answering it. So number theory says if you want to have an error correction scheme, first come up with some way of mapping, drawing a picture of all of the possible permutations of the bit strings that you would like to send. So let's just give them names, right? So let's let A, maybe A equals 10110101. All right, so that's A. And we're going to set B to be close. So it's going to be A with 1 bit changed. And C will be a different bit changed. And D will be another bit changed. And we'll draw dots around here. So the ones that are close to you are close to you in every possible way. They're very similar bit strings as well. And you draw things. So you can map out the whole set of permutations and keep this true for everyone. So a good error detection scheme is designed around the kinds of errors that you see. So with this type of map, you can draw the types of errors that could happen as vectors. So if changing a single bit in a string is a common error in the type of network that you're trying to protect, if that's something that can happen, then these are all possible vectors, right? And if 2-bit errors just don't happen that much, and they're so infrequent that you don't want your error correction scheme to have to worry about them, then you will not draw errors like this, which are 2 bits changed from you. With me so far? Makes sense? And you'll design your error correction scheme to be able to detect errors of bits that change within this radius. Right, so parity does this. Parity can detect a single bit change. This number used to be odd, now it's even. Something's wrong. That's exactly what that's all it can do. Right, check for that. So what error correction code does is, especially the version that fax machines use and that Ethernet uses, they use a cyclical redundancy check, a CRC error correction scheme. You heard of it before? Yeah. So it's a polynomial-based scheme, and it does lots of things in math, but here's the way to explain what it does here. It makes it illegal and removes from the possible list of valid bit combinations all the things around you. It just removes them. You can't send that string anymore. It's not allowed. So if you still need the same total number of strings, you're going to have to add more bits to your packet because I'm going to throw a bunch of them away so that I create distance that requires that the next closest valid packet to A is actually this one out here, or this one out here, or this one out here. So what this will do is prohibit any of the dots that are closer from ever being valid representations. So if an error occurs on your network that changes the bits in your string so that it changes from being A to being here, or here, or here, or here, you'll catch it. You'll detect it. This is much stronger than parity. There's many more combinations that you will detect as errors. Okay? Yes?
But the combinations are complete.
Yep, they're just not part of your valid number space anymore. You can't send them. So you're discarding a big piece of your number space, so you need a much larger number space to compensate for that. So now everybody's further apart from each other. You have no soldiers or no spies who live within 5 miles, 5 kilometers of each other. So if you have 1,000 spies, they can't all fit in Monterey. When they could live all in the same building, it was no problem. They could all be in one place downtown. But now you've implemented this rule, and this is what governments do and large companies. It's called key man insurance policies or key man policies. So you never let the top officers of a corporation fly on the same plane, ever. Because if the plane crashes, the corporation ends. When the President of the United States gives his State of the Union message, everyone is there. All the Congress is there, except for one person. It's somebody on the cabinet who's in the line of succession to become the president if this person dies, and this person dies, and this, and this, and this, and eventually you get down to the cabinet. And so that person is called, anybody know what the name is? There's a popular TV show with Kiefer Sutherland, Designated Survivor. So each year, they designate a survivor. You go far away. So even if a nuclear blast hits the Capitol, you're president. But you don't get to hear Donald Trump speak. I would volunteer for that job, right? And hope to be president. But anyway, what this does is something like that. Force separation between, just from policy. So now it's going to take a huge error to even get out into the range of things that could possibly be valid. So that's the first really strong advancement that CRC gives you. Now, the next thing you have to worry about, which you worried about in parity as well, is of all the valid strings out here that could have been there, and they're not this close together, right? You know that already. This is a 3D graph that I'm compressing to 2D. Of all of the valid ones, what happens if you have an error that takes you out that far? Can you detect it? Most of the time, CRC can still detect it, because if this is a valid one, but somebody picks one here, it's not valid. It won't pass the checksum. You won't get fooled. So every one of these things has a different CRC checksum value. They go through a math algorithm, and the actual bits you're using are one of the inputs to the algorithm. So if you're sending a different packet, of course it's going to have a different checksum. So we're good at doing it, but mathematically it's possible. And it's actually quite common to have a change made to a packet that changes to something else that has the same exact checksum. It's not very likely in numbers, but because of all the packets being sent, it happens more frequently than you'd think. So CRC can, this is really the test of an error correction scheme. Can it get fooled? Can you send an erroneous packet or subject a packet to errors, and Ethernet's error correction can't catch it? Is it possible that on an Ethernet wire, you transmit something, it gets changed to something else, it arrives at the other end, it is corrupted, but Ethernet doesn't think it is? Yes, in 1 in about 4 billion times. So this doesn't mean 1 in 4 billion times a packet gets through. This means of the packets that it thinks are errors, subtract those, and the ones that are good, stack those. But if there is an error that is good but is undetectable, that'll only happen in about 1 in 4 billion errors, erroneous packets. So it's a tiny, tiny fraction, right? So they used that in this paper, and they said, okay, if that's the case, and we're doing, you know, hardware checking inside the routers, like memory parity and stuff like all computers have, then we should be able to see if this is working. So they used a tool like Wireshark, and they started looking for retransmissions. And they tried to look for, you can get hints when you look at things, whether it's a retransmission or caused by buffer overflow versus a retransmission caused by thrown out because of an error. So they figured that out, and they sorted things into packets. So they collected a lot of data, and Stanford sits at the core of the world, at the core of the internet backbone. So they have access to lots of data from packets. And so they just watch and accumulate this data. It was a genius study. I mean, it's one of these when you hear it, it's like, God, why didn't I think of that? Because it's like totally doable, totally doable. And like, now it's gone, right? So what they found is instead of 1 in about 4 billion, they found people retransmitting because of errors about 1 in 1,500 times, many orders of magnitude more frequently. Why? Because we write crappy code. And our TCP code and our IP code is full of bugs that everyone uses. So we mess things up and don't interpret things and don't parse things right, and you know, we're just terrible at it. Inside the routers, the memory is buggy. It has way too many bit errors. It's not very good quality. The power supplies we buy don't give very constant voltages, and that causes errors as well. The RAM drives we use in here to keep track of the data, those things have errors. We're not using sufficient error correction on them. I mean, we're a mess, just a complete mess. So it's like sending an astronaut to the moon in the best capsule possible, and then his hose comes off because it's not plugged in good. Like, or how about this one? Sending a Mars lander to Mars, and the landing team thought you were talking about miles instead of kilometers, and so you crashed the thing into the surface of Mars at terminal velocity. We did that. NASA did that less than 5 years ago. Did you guys hear about it? Yep. $1 billion project, flew this thing to Mars, got there, and just impaled it into the surface of the planet at terminal velocity because they thought they had 25,000 miles to break instead of 25,000 kilometers. That's why it's stupid to not be on the metric system. And they were just like the laughing stock of the scientific community. I can't believe you didn't hear about it. So I just, come on, guys. Really fired. So this software has been improved. The memory, we're more careful about it now, but it's a clever study. And it's not accurate to say there's no error checking. Maybe at this layer there's not much, but there is still the IP checksum is there. You may not check much on it. Okay, flow control is end to end. It's like before you send the truck with 200 heads of lettuce to the McDonald's this morning or to the Carl's Jr. in Paseo Tech, you might want to make sure they have that much room in their refrigerator. So that's flow control. And flow control would be they call you and they say, I need 12 more heads of lettuce. I need 20 more heads of lettuce. I need 18 more heads of lettuce. They're telling you how much space they've got for what they think they need. Congestion management is not flow control. Congestion management is making sure the driver uses Waze to get there efficiently and doesn't get stopped or dropped along the way or stuck in a traffic jam. So that's congestion management. That'll come a little bit later. So why do we say the network layer isn't likely to have, doesn't have flow control? It's not where congestion occurs. So TCP implements flow control and TCP implements congestion management. IP doesn't really, it's not considered a good use of its time for it to do those things. So the upper layers implement buffers to store all of this stuff. So I can show you how this works. We can see it with our own eyes. So I have to open a website that, let me think how to do this. It'll be better if I go to some place. It's just tricky. I never really know where to go. So let's say we go to the New York Times and open that up. This is going to send like tons of traffic. Like that's a shot. Okay, stop. I'll just stop class and start reading it if I see any more of it. It's going to make me giddy with laughter. Okay, can I see any of the New York Times packets? Is that possibly a New York Times packet? I don't know, maybe. Okay, so let's see if we can find what I'm looking for here, which is window size. And if I'm lucky, that will change as I go through here. You see it changing down there in the gray? 2488, 8189, 2488, 8189. We go back 4. Here's 2488, a little different. So this one looks like it's probably the WebEx because they're not changing much. On Wi-Fi, though, they're more likely to change. So let me get rid of that filter and see if we can find other numbers in here. What is this one? Who is that? That looks more probable. Oh yeah, see the window size changing? 235, 4096, 4087, back up to 4096, 244. It's in both directions, right? So there's two sets of numbers. There was a 3000 in there I think I just saw, 3976. Every packet you send data back to tell the sender how much room you have left. That's flow control. Okay, so done with that and ready to move on a little bit to this. So do you guys want to take a break, or are you okay? Can't hear that. Can't hear that. You're okay? All right. You guys okay? I mean, it looks like a couple of you have needed to go take a break, which is totally cool. You want to just leave it like that? Okay. So I think from talking to the prior section, you guys probably have the same classes. You know how to do subnetting. You know what IPv4 addresses are. You know a little bit about classful addressing, Class A, Class B, Class C, but you know, so we don't need to go over everything. Does that sound fair? Okay, so I'm going to walk you through the things that are more detailed that are helpful to know. So classful addressing, it tried to divide up the bits that we had in a different way than we use today. So we use dotted decimal, and I'll talk a little bit more about that when we get to number theory in a minute. But we use decimal numbers to make it easier for us, and the router, of course, uses just binary numbers. Okay, so let me get to number theory. And number theory is covered in this textbook in Appendix B. So, and no one in the class yesterday knew what positional numbering systems were. Have you guys seen those before? Okay, so you would remember that term even. That almost looks like a virus or something, doesn't it? It starts moving across the screen. Will you let me know, please? I don't need my computer to have a virus. Okay, so positional numbering basically explains what you already know, but in a different way, which is that we use the same symbols, the same set of symbols for all of the positions in our numbers, but they don't always have the same significance. So in decimal, we use symbol 0 through 9. In octal, it's 0 through 7. In binary, it's 0 through 1. So it's always the number greater than the last one you see. Right? In hexadecimal, it's 0 through 15, base 16. All right, so what positional numbering says is that it matters the position that the number is in. So is that true? Yeah, so if you only have a single 1 in your bank balance, you'd rather it be over here than be over here, right? Yeah, so that's an example of, like I told you, you already knew it, but you didn't know it with the same terms. So mathematically, the way this works is you take your base. This is no longer a decimal point because you may not be in decimal. You may be in one of these other number systems. You take your base, let's say it's base 8, and you raise it to the power of its position number. This is position 0, position 1, position 2, 3, 4, and 5. And over here, it's position -1 and -2, and so on and so on. So if you give me a number, 163,74026, the value of this is the symbol that you used, 1 times, and its position. And then this one is 6 times 8 to the 4th, and this one is 3 times 8 to the 3rd, and so on. Do you agree that that will result in the correct value? And we'll have some decimal number that we want at the end of it. So this is the way positional numbering works, and as a result, it argues that you do things backwards from the way you might think. And by that, what I mean is, if you're given a number, 62,314,285, and you're asked to convert it to a different base, let's say, like to binary, for example, then what you're going to want to do first is see if it will fit in the highest value position and subtract from it as much as you can, as many multiples of this value you can, and write down how many times it fit here. And then you'll take the remainder and you'll try to see how many of these can you take away, how many whole multiples of this exist in your remainder, and you will write down the number of times it exists here. And then you will take what's left and you'll try to subtract as many of the 8 to the 3rd you can and write down how many times you were able to do that here. So you're moving the remainder to the right, to the right, to the right, to the right. So technically, each position in a positional numbering system is nothing but the remainder left over from the position to the left. So the 6 means this is what was left over that I couldn't take care of in this position, because it wasn't big enough to raise this number to 2. So let's now turn ourselves to IP addresses. What base are we using with IP addresses? Using base 8, base 14, or something else? What are the valid ranges of numbers in an IP address? What's the valid range of numbers? 0 through what? 255? Is that right? You guys agree? What's the broadcast address in IP? It's got to be that then. 255, 255, 255, 255. All right, so if I have 0 through 255 as my symbols, what base am I in? 256. I just showed you it's always one bigger than the one that you're using. So we're in base 256. Normally, for most numbering systems that you and I use, we use a single symbol to represent each one of the possible values. Somebody mentioned hex a second ago. That's a great example of it. Right? For hex, we are okay that we don't have enough Arabic numerals. We just continue on with the Roman alphabet. We just switch centuries and continents. And so we have A through the F, and that's base 16. So anybody here want to try to remember 256 different symbols? If you stick with that rule, that's what you're going to have to do. So you're going to be using every kind of special character you've ever seen in your life, and emoji and everything else. So we said, no, that's not possible for humans. So we'll just keep it in decimal, but each symbol is going to be represented by a number in decimal of 0 to 255. It should only be a single symbol, because what you're going to do is take this value that's here, and you're going to multiply it by what? So if you want to turn this into a decimal number, which lots of websites will do and Wireshark will do, it will show you the decimal version of your IP address. It's a positional numbering system. We're in base 256, correct? This is the first symbol. None of these are fractions, so these are all to the left of the radix point here. So the dots are there just for us. So we can erase those dots for a minute so we don't get them confused. So this is a 4-digit number. Each digit is base 256. Exactly. This one is 256 to the 0. This one is 256 to the 1. This one is 256 squared. And this one is 256 cubed. All right? So the value here is going to be 256 to the cube plus this value times 256 squared plus this value times 256 to the 1 plus this value times 256 to the 0. When would you ever do this? When would you ever use this? Yeah, well, you can, no, you don't need to do it to convert to binary, actually. You can just convert each one independently. It will work. It will work. It will work. It will give you the same binary number, which is kind of blows my mind, but you can just do each number one by one if you want, thank heavens. Right, so that's true, but like as a network manager, why would you ever want to do this? So what's one of the things that you have to keep an eye on as the years go by as a network manager that you can't run out of? You can't run out of memory, addresses especially. As a network manager, that's kind of unique to you. You can't run out of IP addresses. So somebody offers you a range of IP addresses. How do you figure out how many there are? This is how you've been doing it. You've been using websites, probably. You've maybe seen other tricks. May not have realized it. This is the only way you can do it. So if I ask you, give me an IP address. Somebody give me one. Give me the first number in here that's between 0 and 255. Blurt one out. 10. All right. And somebody give me the next one. 15. All right. Let me change colors here. 10.15. Dot what? 88. And dot, give me a big one. 216. All right. Everybody okay with that? So which IP number in sequence was this one to have been given out? If you started at IP address 1 and counted up, which number is this? So you can multiply that out. 10, 15, 88, and 216. So what I'm going to do is pull up my calculator, or my calculadora, since I have it set in Spanish. I'm going to say 10 times, I don't actually know if it'll do this. Let me see if I can, oh, you know what? I forgot. I think I bought the HP, maybe it was on here. I bought the HP 15C. I got so tired of not having it, I bought it from them. They made an app. It was like $20. It was crazy expensive, but it works just like the calculator, so it's cool. So 256, enter 3, x to the y. Let's do that. Whoops. And multiply it by 10. And we get the following number, 167,772,160. And what we want to do is, and I'm not going to do it for you guys because it'll take too long. We did it yesterday, but I think I don't think we needed to. We'll divide it by 256 to the cube. We will take the lower value of it, depending on the language of Excel you're using. It can be trunc or min or whatever. But you're going to come up with an integer number out of it, and you can work backwards. You can get the number there. So if somebody then hands you a different IP address, that's, let's say, 94 and 30, if I give you two IP addresses, 10.15.88.216 and 10. Let's say 16.94.30, how many addresses do you have in that range? Anyone? No one? It's not obvious? Yep, so this is how you would do it. You can convert it to a decimal number like this and subtract the two numbers from each other and have your answer. If somebody tells you this is your starting address and you can have 1,638 addresses, how are you going to know how to do it? Convert it to decimal, add 1638, and convert it back. And so positional numbering is very handy when dealing with IP addresses. So this goes through it a little bit more in a couple of slides. There's textbooks on this, like that's a surprise. But, and in fact, this is what they did, was they added stuff. The only thing you have to watch out for are overflows. So we'll take a peek at a couple of things that computers use, that routers use to convert, but we'll build up to it, and we'll get to overflow, I think, in here somewhere. So everybody knows what NOT does. It's a logical function that just flips bits. Ones become zeros, zeros become ones. So if I apply a NOT operation, it'll turn a 17 into a 238, and a 121 into a 134, and a 14 into a 241. By looking at those decimal numbers, does it look like we should have been able to figure that out ourselves? Like, does it make sense to anyone that the complement of 17 is 238? Like if you subtract 17 from some number, like 255, you should get 238? Do you? Yes. Yep. 17 plus 238 is what? Thank you. What is 121 plus 134? Oh, you so smug. You add so fast. What about 14 plus 241? Yeah, she's good. And I suppose 35 plus 220 is also? So this is helpful to computers. You'll see in a moment when we start trying to figure out whether we need to forward a packet or not. And take one string of bits and only give you the value of the first input if the value of the second input is a 1. So if you give me an IP address, for example, like 110.10.1110.1110.1101, and I tell you, this is not 32 bits, but I tell you it's a /10 address. If you remember, what that means is the first 10 bits are network number, net ID. So from here, 1, 2, 3, 4, 5, 6, 7, 8, to here, our net ID. So you get a packet at the router, and it's got this IP destination address in it, and you need to figure out, are you supposed to route it or not? You can't hand this IP address to your forwarding table because it doesn't have an entry for this address. It only has network numbers. It doesn't have 4 billion entries for all the IP addresses. So you need to figure out how to turn this IP address quickly into a network number and it with the inverse of its subnet mask. And what you'll get out of it, in this case, is the host number. If you AND it with the network mask, then this would be zeros on this side. It will zero this out, and all you'll be left with is a network number, and you hand it to your routing table, and it will tell you if you need to do anything with it. So this is how the computer actually, this is how the router actually pulls this off. So they will AND with the subnet mask you give them, the IP address that showed up for your destination, and consult their forwarding table. So it makes sense, doesn't it, that they don't do more complicated math than that? It's just simple bitwise operations. So they walk through an example of this. I'll give you a problem to kind of help you guys work through this. OR does the same kind of deal. So with OR, we might be trying to come up with the network number. So let me give you an example of when you would use OR. So I'm going to draw a network for you, and this was really hard for the class yesterday. So I'm hoping you show them up. Yeah. Yeah, it was hard for the class yesterday. So let's see if you guys can figure it out. So this PC sits on network 8.3/16, and this server sits on 121.242.3, no, let's make it dot 130.0/24, okay? So 24 bits in is the dividing point here, and for this one, it's 8.3.0.0. It's here, correct? If you want to send a packet to this guy, and his address ends in a .2, what destination address do you put in your packet? Yeah, 121.242.130, which is the network number, and his host ID is 2. So what you're doing is assembling the net ID and the host number. And the reason why you have to do this is because this router, when he receives the packet, he's going to AND the subnet mask with this, and the 2 is going to fall off, and you're going to be left with this, and he's going to look in his routing table, and the routing table is going to say, you know, of all the routers I can get to, forward it to this guy. And he's going to do the same thing. And when it finally gets to here, he's going to know it's on the LAN. Right. If I want to send a broadcast out of my PC, what address do I use? You said it earlier. Yep. 255, 255, 255. So here's the question. How far will that go across this network? And I don't want you to guess the answer. I want you to walk through exactly the same steps we just did for this other packet. What's the first thing you're going to do? AND it with the network number. What's the network number for this? Well, I'm not sending anything over to the right necessarily, but what's the subnet mask for this? Do we know? Well, if it came from a computer, it'll probably fill in a subnet mask. It's given the space, so let's say it's 16. So what's that going to turn this into? When I AND 1111111111111, that's 16 zeros, zeros with this number. What am I going to get? I AND the 2 together. Yep. Right, now it's ready to go to the routing table inside my router. Am I going to have an entry for this network? Like what website do I pull up when I go to 255.255.0.1? Who owns that? Who owns that network number? Is it Amazon or Microsoft? What's your intuition tell you? Who owns this network number? That's exactly what it is. It's a special network number. It's not routable. You will get no answer back from the routing table telling you where to send this, because there is no place to send this. It's valid, but it's not routable. So let me ask you again. When I drop a packet on my LAN with this IP address, how far across this network will it go? Just in the local LAN. So if I want to send something to every device on this network over here, an update, I'm McAfee, and I have a service contract to keep virus patches on your machines, and I want to send a broadcast message out to all your machines to wake up and come pull down the latest virus patch because there's an emergency patch for a bad virus that's going around right now. What address could I use to broadcast across the network to everybody on this LAN? (121, 242, 130, 255). Set the host bits to that special range. So how will this get routed? I will apply the network mask, and when I do so, I will get 121.242.130.0. I will go to my routing table. I will look to see if I have an entry for that. I do. it says send it to this router. I do the same thing here. This router says it's ready to drop on the local LAN. It's a special broadcast address, so I'll use the same hardware broadcast address of all Fs. Ethernet will do that for me, and I will drop it out the door. So it goes out like a bomb. It will hit everybody on there. So if I need to send a broadcast to these guys, what would the address look like? Instead of sending this, what could I have sent? You're going to have to do it again. Instead of sending this, what could I have used to reach everybody on this LAN? .0? Why .0? And so why did you change your mind?
Because I saw that you have 8.2
/16, right. Makes sense? Just set all the bits to 1, and it turns out to be 255, 255. It's a lot harder when the dividing lines aren't 8, 16, and 24, and they almost never are. But, you know, that's why we build software, right, to help us with that. So all I really needed to do to get everybody's attention on my LAN, at least everybody that was part of this network, was to send this address. It would have done exactly the same thing. So how do I figure this stuff out? I can OR this with 1s and turn it into 255s if I want, or I can OR down here and turn this into 255s. And then just leave these as zeros, and you'll just get out of it if you OR it with all zeros, just the same thing you put in. Right? You OR something with 0, it doesn't change it. Right? So that's a piece of logic of why we do something like that. All right, let's fly a little bit through classical addressing. This is how we thought we needed to divide things up to last for eternity, and it was a big waste of numbers. But, you know, no one could have ever imagined it was going to grow this big. I'll give them a pass this time on it. This is another thing we did wrong, but it seemed okay. It's unfortunate that we didn't feel like we had more computing power than we would. So here's a fatal software developer flaw that all of you have the opportunity to make all the time. It's to design for today and not for what's coming. Anybody play soccer? Where do you kick? If you're trying to pass to the wing who's running up the side, where do you kick the ball? To the wing? To where the wing will be. Correct? That's exactly the way you should write your software. Write your software to where computing power is going to be. Lots of software developers get caught in Moore's Law's trap, which is they design for the computing power they have now. They can't imagine being able to pull off what they're being asked to do because there's not a CPU fast enough. Just wait. When does this need to come out? So when you're designing the Apple iPhone, there isn't a chip nearly fast enough to run the software that you are emulating on a server. And an iPhone emulator running with a very powerful Intel server chip, but you're not going to put that in your iPhone. How is this going to work? Well, wait. The ARM chip that they're developing will give you just enough power to do that. So the people that decided how much speed should we emulate that we're going to have were like this with the hardware scientists and telling them, you got to shrink this chip more, you got to get this down to however many nanometers, I got to have this clock cycle. You got to give me this clock cycle or I can't use the software my guys need to write. And so you figure out what clock cycle you're going to use, you give it to the emulator, and they write everything to work smoothly at that speed, with a processor with no more speed than that. And then when it's time to actually build the iPhone in 18, 24, 36 months, I mean, who knows how long they've been working on it, then you're there. Because you're kicking the ball to where the player will be. So it's a fatal trap that people make all the time. So you can make, this should have applied to this diagram. Yeah, we don't have that many now, but let's at least, we don't have that much computing power. That was the real reason they decided to do it this way. They didn't feel like they had the ability to track more than that. And for that reason alone, they misjudged it. Okay, so you got Class A's, B's, and C's. Here's a few fun things you may never have noticed. All Class A's start with the first bit of 0. All Class Ds start with the first bit 1 and the second bit 0. Class Cs have the third bit 0. Class Ds have the fourth bit 0. Did you ever know that? So it's really easy to build a tool to figure out what class you are. That tells you what subnet mask to use and what to and, or, and not with. Right? So you just check where you see the first 0. And that gives you your information you need. Then you can set all those values. Okay, we all know this thing is divided up 8, 16, and 24. That's basically all there is to really learn here. There's some special addresses that we need to look at. There is one bug in one of these tables that I need to, Forzon, this book was written a while back. He's not gonna fix it, but this should be 239, not 299. He apparently was hoping something was on sale that day. Only $2.99. So that one should be. I don't know why I never just corrected, but let's just do it now for all of eternity, so that all of my classes from now on, we will all be able to think of you, this class. All right, and we'll make it a little thicker. Hello. Thank you. Glad you can make it to work today. Okay, and yeah, that's enough. Okay. We good? Makes sense? Learn some new stuff? We talked about what's inside of IP. We talked about fragmentation. We talked about how routers really do use these things and calculate whether they need to route something or not. It's actually simple and fast, and that's kind of comforting, isn't it? I mean, it's done kind of at the chip level. You don't need a bunch of software. You don't have time to run software in a router. A couple other things that probably nobody's mentioned is when you calculate your routing table by running your routing algorithm and you crank out your million-line routing table, however long it might be, they're big, you just have impossibly less time than would be required when a packet shows up to consult the table. It can't be done. You can't start looking through the table to see if there is indeed an entry for this network that this user is trying to go to. So what we do is use a reverse type of memory called content addressable memory. And what this does is basically have each entry in the memory do a simultaneous search across every word in all of the RAM to see if there's a match. There's no Newton's approximation or bubble sort or any way of trying to find whether the value is there or not. You just ask every location, are you it? So this would be like having everybody in the auditorium stand up and sit down as I call out the lottery numbers. You guys have seen people do things like that before. First number is 3. People sit down. The 3s are still standing. Next number is 4. More people sit down. Next number is 9. One person standing. They're it. So what content addressable memory will do is let you feed it a string of bits, and all of the words are being searched simultaneously. And it's kind of different from what we would normally do. It's very expensive, and unfortunately it competes now with server technology for that memory. So there's a worldwide memory shortage, and has been, that delays the shipments of everything. And the Fukushima disaster started the problem, and it just went downhill from there. Then somebody decided we could use a lot of that memory in servers as well. So that memory is on every input line card on a router, on the fast routers. So you have a copy of your routing table on every card. It runs in hardware. You don't have time to consult software. So as the packets come in, they could come in, at millions a minute. You don't have time to do anything else. So if you have a 10 gig or a 40 gig network, 40 billion bits a second, divide that by average packet size, 40 E9 divided by 1500 times 8, 3 million packets a second. A second for each line card coming into a core backbone router. So these core switches like Nexus 9000s, they can cost $500,000. And people will pay it all day long. They're that important. They're that expensive. Okay, so I told you some fun facts. Did I show you guys the Nexus chipsets and tell you the story about that? Okay, so it'll be the last thing and then we'll go. Now we're going to have some fun. Whoops, don't do that to me. That is not the mejor resultado. My entry for Nexus was the mejor resultado. Why does it think it had something better somewhere else on the internet than what I already had? Okay, so let me take a peek. Okay, so I got to go to Cisco Live in Cancun a couple of years ago, and there were, I don't know, 2,000 customers, something like that. It was a big deal. And I was there with a person who needed some help trying to understand what people were trying to say. And my friends at Cisco Mexico City lied and told them I was fluent, which I wasn't. And so I got to go because they really wanted me to just hang out with them, right, at Cancun for a few days, which we did. And we had a lot of fun, but we worked. So I had to translate for this Indian guy, which was a little awkward. But he didn't speak a word of anything, including English, because I could barely understand him, because he had a very thick accent, and it's hard for me. Nobody else seemed to have a problem. That was my problem. So I was at this table, and I was right to, like, where I'm standing was my booth. And I turned to the right like this, and there's a Nexus switch there for customers to see. It's not in a glass cage or anything like that. It's sitting out. It's got line cards that come out, and so people have been taking things out and stuff like that. And it sits on this rotating little thing so you can spin around. It's not plugged in and has no cables or anything. And, you know, I think, oh, demo equipment. You know, it's like a defective unit or something like that that they send. Because, you know, this is a $100,000, $150,000 switch. Like you would never leave that just like sitting out like this. That would be stupid. So I convinced myself that it was surplus, you know, garbage. So I got kind of interested in it, and I was teaching computer architecture at the time. In fact, I taught one course live, including this very Nexus switch. And what we did was I started showing, you know, all the heat sinks, all the radiators. Those look like radiators in a car, and those are all to dissipate heat. And I took some pictures. Finally got a good one. Yeah, took some pictures. Let's see what else I have in here. Here we go. Now we're getting to the fun stuff. Then I started looking at who made the stuff. Foxconn, of course. They make everything, including for Cisco. Cisco's never owned a manufacturing line. And we looked at the type of memory they have in here and the RAM cards, and it's different also. And then I started to look for kind of the brains of the outfit, because we buy a lot of merchant silicon, which is the name you give for chips that are already made that you can buy, anybody can buy. But the secret sauce are in the custom ASICs, the custom chips that we design and build and supply to Foxconn to add to the board. So those are the trade secrets. Secrets are inside those chips. Fortunately, it's very hard to reverse engineer a chip, but that's what we send. So it had a big heat sink thing on it, and it had this heat conductive paste that would allow heat to pass through. So I just ripped it off. I pulled the top off and exposed it, and started showing off like, well, here's what this looks like, and we can take a look at what some of the other stuff looks like, and we pull it off, and here's some other chips in here, and I kind of put it back together. You can't really reassemble it back unless you have this adhesive, and it's cheap. You can buy it, but I didn't have any with me in Cancun with my swimming suit, so and this thing was built in Canada, where they don't steal all of your intellectual property, so I didn't have any with me. So everything goes fine. I mean, I'm taking this thing apart, and I'm pulling heat sinks off and putting things back, remounting them, but I don't have the glue and stuff. And we leave, and about 8 days later, a mass email goes out to everyone who attended for Cisco at Cisco Live. Who the hell ruined my Nexus 7700 from my lab? And my product manager immediately emailed me, goes, don't worry, your secret's safe with me. And I'm like, oh my God. So yeah, I ruined a $150,000 switch. 3 million peso switch. Like, yeah, it was easy.
What does
For doing everything we talked about today. It's a high-speed switch.
So like you would just break that up. Like
You'll use it in a data center or at the core of a big company, right? In their data center. It's a high-speed data center switch. So yeah, my brush with death. So anyway, I made it to retirement. I didn't get fired for that. So thank heavens. All right, guys, thank you very much. That's all I had for you all today. And I will post, I need to get grades posted up for you guys. It may take me a day or so because I'm struggling to get my exam prep done for the other class. I made you guys the priority over them last week, and I got to give them a little love now. Yeah.